All right, now that we've gone through Module 12, I want to put forth a PowerPoint here that sort of puts it all together, kind of like we will have when you take the test over these modules 12 and 13, and basically modules 10 through 13. And here I want us to put all these together into one, kind of like we had in 12.3, where they threw in a few where you could use either the T or the Z, and you had to decide which one was the correct one to use. So let's review some of the strategies and some of the things we want to look for when we're doing a hypothesis test. So we've looked at the theory and the logic behind our hypothesis test, and now we want to look step by step at the strategy we want to have in actually doing the test itself. So the first thing as you're reading through a problem is you want to ask yourself, what kind of parameter am I measuring? There were two main population parameters that we measured. One was for population mean, and then the others were for population proportion. Of course, the formulas that we use to calculate our test statistic and that type of thing are different when we're doing proportions versus means. For example, in a proportion problem, you're probably not going to be given a standard deviation because we don't need it. So it's very important to discern and have those kind of separately written down, ready for use, depending on which population parameter we're measuring. All right, so when we had a mean, and that was the number of interest for our hypothesis test, the next question you want to ask yourself is, do I know the standard deviation of the population? In other words, are you given a sigma value? If that's the case, then we would use the standard normal curve Z, and we would use invert normal CDF on our calculators. If we do not know the population standard deviation and instead are given sample standard deviation, which is S, then we are going to use the T distribution curve with S as our estimate of sigma. And so then also on your calculators, you would be doing TCDF and invert T. So very important, it's important to discern if you know the population standard deviation or if you know the sample standard deviation and are using that as an estimate of sigma. If we're doing a proportion, as long as n times p is greater than or equal to 5 and n times its complement is greater than or equal to 5, and this of course will be the case for all of your problems, then we will always use the z-table in a proportion test. After you've established this, you're now ready to use your test using one of the two strategies, either the critical value approach or the p-value approach. You need to be familiar with both of these for the exams. I will have some set up for one and some set up for the other. So if we're testing for means, we're going to start off with one of these, and we want to take the critical value approach to the problem. The steps that we take are as follows. Number one, we want to establish the null and alternative. That's actually the same for both approaches. We always determine those first. But then we differ a little bit in our approach. On number two, when using a critical value approach, we determine what are the critical values. These are boundary values for our rejection regions, and our rejection region will always have a area equal to our significance level sigma. Then we want to draw a picture of this. So we want to draw a graph and label it with the critical value or the critical values if it's a two-tailed test. And number four, we gather our data, we determine the value of our test statistic, whether it's a Z or a T, and then we draw a conclusion based on the value of the test statistic compared to the critical value. So notice then in the critical value approach, we are comparing two z-scores or two t-scores to determine whether we're going to reject or decide to fail to reject the null hypothesis. So let's look at an example. Computer program designer has developed an online questionnaire she believes will take an average time of 15 minutes to complete. Suppose she samples 35 volunteers and finds that the mean time to take the test is 14 minutes with a standard deviation of 2.5 minutes. I'm sorry, we had a little problem there. So let's start this over again. A computer program designer has developed an online questionnaire she believes will take an average time of 15 minutes to complete. Suppose she samples 35 volunteers and finds the mean time to take the test is 14 minutes with a population standard deviation of 2.5 minutes. Determine if there is sufficient evidence to conclude that the completion time of the online questionnaire differs from its intended duration. So in the wording, we see that the questionnaire differs from its intended duration. That would suggest there is no direction for my test. So in my null and alternative hypothesis, we would say that the mean time is 15 and the mean time is not 15 minutes because the word differs there. Notice also, if you're trying to decide which one is the population number, which one's your sample number, X bar is always going to come from the sample. And here we see that the 14 is really reflective of how the 35 volunteers responded. It isn't the status quo that we're assuming. All right, so then we determine what our critical values are for a 0.05 significance level. Because we know the population standard deviation, we are turning to our z-chart because we know sigma. This is a two-tailed test with an alpha equal to 0.05, and the z-values for that would be positive and negative 1.96. So these are the two boundary values that in order to reject the null, I need to have a sample that's extreme enough such that it passes into the rejection region. So these are my boundary values. Notice I haven't pulled anything from a sample or anything like that. My critical values come directly from my significance level, which tells me the area of my rejection region. Then we run our test of our test statistic. And we do this by plugging in 14, comparing it to 15 over the standard deviation sigma over the square root of 35, and we get negative 2.37, which is over here on the left. We can see that it did surpass the bar that I set. It fell into the rejection region, and so therefore we reject the null, and we say there's sufficient evidence to conclude that the average time indeed differs from the assumed 15 minutes. So my description is in rejecting or failing to reject the null, and then we talk about whether there's sufficient evidence to, and then we describe the alternative. For proportions, let's take another look here. In a sample of 88 adults selected randomly from one town, it's found that 4 of them have been exposed to a particular strain of the flu. At the 0.01 significance level, test the claim that the proportion of all adults in town that have been exposed to the strain of the flu differs from the nationwide percentage of 8%. So again, we got the word differs here. So that would suggest that not equal to is what belongs in my alternative hypothesis. Now, for my test statistic, it was found that 4 out of 88 adults suffered from the flu. Now, we're going to come back to that here in a minute. The step 2 is to set up our world here, our world view, assuming the null to be correct, and having a significance level of 0.01. For a two-tailed test, we look on to our t-chart and go up to the z-value for significance level 0.21 and 2 tails, and we see that the critical values are positive and negative 2.576. We draw a picture to visualize this situation. So again, we're running a two-tailed test. We split up alpha into 2 tails, so the total of these tails is 1%, 0.005 in each tail. Now we calculate our test statistic. Now here, I would have instead, I put this in as a decimal, but it's probably better that you just take 4 out of 88, just do that division, so that you don't have any rounding issues on these. It tends to be, especially in this section, a little bit picky when it comes to the proportions and rounding. You don't want to round too early. So if it's a decimal that continues to repeat, go ahead and just put the fraction right in your calculator. Go 4 out of 88, subtract 0.08, hit enter, or put that in parentheses. We get negative 1.195, which is right about here on the normal curve. This tells me that my sample data was not extremely different enough for me to reject the null. We do see a difference. 4.5% is definitely different from 8, but for such a small sample of 88 people, it wasn't different enough. And so we failed to reject the null hypothesis. We're all about getting extreme values in our sample that differ widely from what the null is assumed to be. This 0 goes with the 8%, and this negative 1.195, this goes with that 4 out of 88 value. And we see that the two don't differ enough, because here's the area where I would expect my test statistic to fall if indeed the null really is true. And so it fell right in that area. We have a 99% level of confidence, and so we fail to reject the null on this ground. All right, so here's another example. A manufacturer is responsible for making barrels to store crude oil for the United States, which federal requirements state must hold 42 gallons of oil. As part of a routine quality check, you randomly select 27 gallons off the assembly line and find that their mean capacity is 41.7 with a sample standard deviation of 0.8. Can you, as a quality control administrator, say with 99% confidence that the requirements are being met? All right, so my value that I am going to assume is true is this 42. Unless, remember, this 41.7 came from my sample, so this is my comparison to test this one. We, as a quality control administrator, are wanting to make sure that the requirements are being met. And so we're going to assume that they're 42, and then we're going to see if my sample data differs enough from that. So my null hypothesis is that requirements are being met. They equal 42. And then if they're not being met, they're either too small or too large, so we say mu is not equal to 42. So it's a two-tailed test again. And my critical values, this is for a 99% confidence level with two tails. And so again, we have that 0.005 in each tail, splitting at that 0.01. And because this is a t-test, given that we used a sample standard deviation of 0.8 gallons, we go to 26 degrees of freedom, one less than my sample size, up the column for a two-tailed 0.01% or 0.01 significance level. And these are my critical values. So these are t values. And when I go to measure my test statistic value, it's going to be a t-value. Notice that we've put s in here instead of sigma, and therefore we use t. All right, and we get negative 1.949, which is almost 2 standard deviations to the left. However, it is not, according to the significance level I set, significant enough for us to reject the null and say that the requirements are not being met. And so our conclusion is to fail to reject the null hypothesis. Based on the sample, the manufacturer can be 99% confident that the barrels fall within the necessary standards. All right, so the first one we used z with mean. The second one we used proportions, so we also used z. But on the third one, we were not given the standard deviation of the population, and we're forced to use the sample standard deviation instead. And so we appropriately used t. Now the p-value is just a different approach, but the same basic idea. We have a test statistic that we're pulling from a population, a sample, and we are testing to see whether that sample is extreme enough. But we, instead of comparing z-values in a p-value problem, we compare areas. The steps in performing a hypothesis change slightly for the use of the p-value. We still have the same thing first, but then we go straight to deciding what my level of significance is and gathering my data. So we choose our level of significance, and then we go for our test statistics. So we start gathering data right away. We do not worry about the critical values or rejection regions or critical regions at all in a p-value approach. We just simply want our test statistic and we want our p-value for that statistic, which is step 4. And then our goal to reject the null is to get a p-value less than our significance level so that we can reject the null in favor of the alternative. Then we draw our conclusion based on the above comparison. So Wikipedia, a free online encyclopedia, reports in 2006 the average American woman is 25 years of age at her first marriage. A researcher claims that for women in California, this estimate is too low. So surveying 213 newlywed women in California gave a mean of 25.4 years, with a population standard deviation of 2.3 years. Use the 95% confidence level to determine if the data supports the researcher's claim. So in this case, we would actually have an equals here. The mean of the population of women, the mean age, is assumed to be 25 unless we can prove otherwise. But looking up at the wording, we notice that the researcher claims that for women in California, the estimate is too low, meaning she believes that women in California have a higher age when they first get married. And so that is a greater than statement, so we would say mu is greater than 25. Now, my test came up with a value that was larger than 25, so we know it's going to be here on the right. And then whatever that test statistic value is, we're going to find the area of the right tail. So we put in our numbers, and we run our test, and we see 2.54 is the magic number. So again, this goes with that 25.4. This is 0 here represents 25. And with a test statistic of 2.54, if we look at the area to the right, which we're not going to double because this is not a two-tailed test, we get 0.0055. And since that is less than 0.05, our conclusion is that we are going to reject the null hypothesis. There's sufficient evidence at the 0.05 level significance to suggest that the average age of newlywed women in California is higher than the national average. If the p is low, the null must go. That's something you can always remember. But it has to be lower than your significance level, and that's the key. The lower we go, the more evidence we're presenting that the world is not made up like we thought it was, that 25 is not at the center, but rather in California. The average is probably more to the right of that, a little bit higher than 25. We're not saying it's 25.4. That was just our sample data, but we are using that to show that in California it is slightly higher. All right, a local high school board has been advertising that at least 65% of voters favor a tax increase to pay for a new school. A local politician believes that that less than 65 of his constituents favor the tax increase. To test his claim, he asked 50 of his constituents, and 27 said they favored the increase. If the politician wishes to be 95% confident in his conclusion, does the information support his claim? So here our proportion is 0.65 unless we can prove otherwise. Again, you should have an equals there, not a greater than. Again, different books differ on how we lay these out, but for our purposes, we're always just going to make the null equal to 0.65. That's centering 0.65 on my normal curve. And we're checking to see if possibly less than 65% favor this tax increase. Alright, if we do this little test, and this isn't something you have to do, but it is something that we use to show that yes, indeed, our sample and probability are close enough and greater than 5 so that we have a much more normal distribution here of our data, and that we can use the z-curve. Alright, so we're okay to proceed then. P hat in this case was 27 out of 50, which comes out to around 54%, 0.54. So we compare that to 0.65. We're using proportions here. And our result is negative 1.65. The p-value is going to be the area to the left of that. So if we look that up and use TCDF on our calculators, that will tell us the area of that, which is 0.0516, which of course is greater than 0.05. Slightly greater, right on the cusp there. But because it is greater, our conclusion is to fail to reject the null hypothesis. There is insufficient evidence at the 5% significance level to conclude that less than 65% of his constituents favor the increase. We aren't saying that it's wrong. We're just saying there is enough evidence to reject it. And that's an important distinction to make. Sarah, a university junior, chose to live on the honors floor of her dorm because she was told that the girls on the floor would be quiet and studious. In fact, Sarah was told the students on the honors floor study at least 11 hours per week. After living on the honors floor for a few months, Sarah is convinced that the students on her floor study less than 11 hours per week. Tester claims Sarah pulls 10 girls on the floor. Test Sarah's claim given the results below at a 10% level of significance. So here's our results. From the 10 students she talked to and the average number of hours per week that they study, we can put these directly into our calculators and pull up our one variable statistics. However, our null and alternative, she believes that they study less than 11 hours. The null hypothesis is that it is equal to 11 at least. This is a left-tailed test, and we get negative 1.383 from our statistical data, and then running our t-value. So this is our t-value, this is using the critical value approach. Sorry, I was thinking we were doing t-values. This is the t critical value, and then here is my test statistic value. I got out of order there. So we see that with this critical value of negative 1.383, that my test statistics surpassed that and fell into the rejection region. And so our conclusion is to reject the null. It appears there is enough evidence to suggest the girls on the floor indeed study less than 11 hours per week. As you're writing these things out, it's really important that you get used to seeing kind of these steps, picturing this with a curve, and taking the right approach given the problem that you're being asked.